Right. So we were talking about catalysts made from platinum nanoparticles, and we had a very simple formula that we derived for the specific surface area as a function of size. And I just want to show you that commercially available carbon-supported platinum catalysts are very close to what you would predict based on the simplest of equations, which was specific surface area equals 3 divided by rho r that we derived last day. So here's some catalysts that are available on the Johnson Matthey website. And what we want to look here is at a couple of things. First of all, the platinum loading in weight percent. So this one has only 9% loading, 9 to 10% loading. This is about 40% loading, this one. And this one is about 56% loading or so, roughly. And then we want to go down and find the specific surface area. So 105. And then we want to find the particle size, 3. Okay, so this one has 105 meters squared per gram and 3 nanometer. This one here, higher loading, has 60 meters squared per gram and 4.5 nanometer diameter. So let's just go back to our slide on the previous page and take a look and see where these might be. So 60 and 4.5, 103. So 103, pretty good. And 60 and 4.5, okay? It's like bang on. It's like these little nanoparticles are just little spheres of platinum decorating the surface of carbon black. It's crazy. It's nice to have something work so nicely. So any questions about this? Okay. Yeah, so when we got involved in our fuel cell work at the very beginning, probably around 2002, 2003, both Dave Stevens and I had a lot of experience with carbon. And we got a little bit concerned because imagine if you're putting the best catalyst in the world on the surface of the best fuel in the world, in the presence of the best oxidizer in the world. That's what's happening on the air side of a polymer electrolyte membrane fuel cell. We've got platinum sitting on carbon in the presence of oxygen. And we were wondering how stable this actually was. So Dave started some experiments, and you've got to appreciate these experiments here. It's incredibly tedious. So he had a whole bunch of platinum, carbon-supported platinum catalysts with different amounts of platinum loading, so 5% all the way up to 80% platinum by weight on the catalyst. And he had little containers of these catalysts that sat in an oven at 150 degrees C. And then every few days, he would go off and measure their weight. So at the beginning, he was measuring it daily, more or less. And then later on, you can see, this 2,500 hours is about 3.5 months. And he tracked the weight of these catalysts over time at 150 degrees C. And you can see that with 80 weight percent platinum, you lose almost all your carbon in 500 or 600 hours. It just burns away. Now, if you have any experience with carbon and graphite, and you heat it at 150 degrees C in air, it doesn't do a damn thing. But in the presence of a really good catalyst, it just reacts and creates CO2. So we were really quite blown away by this. And you can see that only the samples that had, here we are with 20 weight percent, not much is happening. And at 10 and 5, they're pretty stable. There's not much weight loss going on. We just don't have enough catalyst there. So people in the fuel cell business didn't appreciate this particular issue, and it led to some interesting stuff, which I'll get to as we go along in the next couple of slides. So then we thought, well, wait a second now. Not only are you in the presence of air, carbon, and platinum, but you also have humidity, because you've got the water that's being created in the fuel cell. So Dave did the experiment again where the oven was held at 15% relative humidity. Okay, so 150 degrees C and 15% relative humidity. That's quite a high moisture content. But then you can see that even the 5 weight percent sample is degrading pretty rapidly, under these humid conditions. So the question was, okay, this is happening in a period of a month or so at 150 degrees C. How fast does it actually happen in a fuel cell running at 80 degrees or 90 degrees C? And you have to think for a minute about, okay, well, fine, what even happens if you have carbon consumption? I mean, who cares, right? The platinum's still there, this catalyst is still there, so does this even matter? So I was a relative newcomer to the fuel cell field, and I think it was 2004. I went to the Fall Electrochemical Society. Somebody invited me to give a lecture in the fuel cell section. So I had never even met any of these people before. When I was giving an invited talk, I talked about this stuff, and the audience was shocked. They couldn't believe that the carbon was so unstable in the presence of the catalyst, to the production of CO2. It's a very low temperature here. So what's the deal? This slide isn't really too important. It just shows you the initial slope of these curves and these curves, comparing the initial slopes in the dry and humid case. So what you're seeing here is that the initial rate of reaction in the dry case in solid, it's about an order of magnitude lower than for the humid case. And two different carbon supports were being studied here. XC72 is a fairly low surface area carbon black, maybe 250 meters squared per gram. And Black Pearls 2000 has 2,000 meters squared per gram. And if you remember back to one of your earlier homeworks where you calculated the specific surface area of graphene, it's 2,600 meters squared per gram. So this Black Pearls 2000 is about as high a surface area as you can possibly get from a carbon black. And you can see that the degradation rates are much higher on the high surface area carbon than on the low surface area carbon. It's the same vertical scale of the two graphs. Yeah, so then what we did was we said, okay, why are these corrosion rates so rapid? And one of the things about carbon of a small size is that the surface of the carbon has unsatisfied bonds. You've got surface functional groups there, like carboxyl, C double bond O, all kinds of different things. And what we were thinking is that, you know, these carbon atoms that are in an unsatisfied bonding condition are more prone to being reacting with oxygen in the presence of the catalyst. So what we did was we took Black Pearls 2000. You can see the weight change versus time for Black Pearls 2000 at 150 degrees C and humid air. And we took the Black Pearls 2000 and gravitized it. So we heated it up to about 2200 degrees C. And then we had the catalyst supplier put 50 weight % platinum on it. And you can see that the corrosion rate slowed down enormously compared to the non-gravitized material. The surface area reduced a little bit, but mainly the idea of doing this was to try to, you know, create a carbon with more satisfied bonds at the surface where you would have less reactivity. So this gravitization of the carbon became a fairly important step in the production of these carbon-coated catalysts for fuel cells. So what's the deal here, okay? Why is this important? Well, this is a sort of a picture of what you have. You have the polymer electrolyte membrane here on the right. And then you have these carbon particles with the little platinum nanoparticles shown as these tiny little circles on their surface, okay? And how does a fuel cell work? Well, you got to have the proton coming through the membrane. This is the air side. Proton coming through the membrane here. Here comes the proton. The electron has to come through the carbon fiber paper, through the carbon black, to the surface of the catalyst. Okay, and you want the proton, the electron, to combine with oxygen to make water. So that means the oxygen in the air has to move through this carbon fiber paper and also appear at the same place. So you have to have electron, proton, oxygen right at this catalyst surface all at once. And that's called the three-phase boundary. You have to have a contact to the proton, the electron, and the gas. Right. Now imagine that where the catalyst particle is touching the carbon, that carbon is slowly burning away. Like I was showing you, it's making CO2 because of the reaction between the oxygen and the catalyst particle. So as the carbon burns away, you lose electric contact to the catalyst. And once you lose electronic contact to the catalyst, you can't have the proton and electron and oxygen in the same place at the same time anymore to make water. So if you have carbon burn-off happening, it's a bad thing in a fuel cell. So on the air side, if you have carbon burn-off occurring, the fuel cell performance will just drop like a stone. Is that clear? Any questions about that? All right, let's talk about flooding. It says we should talk about flooding also. Well, imagine you have the proton, the electron, and oxygen coming at this place where my laser is, right at this catalyst particle. Well, that's where the water is produced. The water is produced right there. And if you get a ton of water around this catalyst particle, then you can't get oxygen to it anymore. And that's what happens when the fuel cell floods. So again, the fuel cell will be unable to deliver any current once it's flooded. And then you have to flow air through it to evaporate all this water and then the fuel cell will become operable again. Look at these catalyst particles back here. Is there any way a proton can get to them? There is no way a proton can get to these catalyst particles back here. So these catalyst particles back here are wasted. All that platinum, which costs a ton of money, is doing nothing. Because the protons can't get to these guys. So it's important when you put the catalyst layer onto the gas diffusion layer that you also include Nafion ionomer, which is kind of like a binder, so that you have a proton path to the majority of the catalyst particles on the carbon black. Otherwise, the platinum's wasted.
Hey, Jeff. So
Yeah.
you talk about the running temperature of the fuel cells pretty high, right? I remember correctly, it's about 100 or even 150 Celsius. At that high temperature, will the produced water that evaporates, that removes the water from flooding?
No, the fuel cell's operation temperature is more like 80 or 90, not so high as you're talking about.
Okay, thank you.
You know, but still, at 80 or 90, the saturated vapor pressure of water is quite high. So you can have a lot of water content in the air before you condense liquid water. But still, it's possible to condense liquid water if you can't get it away fast enough from the particles. Okay, so here's an example of the importance of graphitizing the carbon. So this is some work that was done at 3M. So what they did here is they exposed a cell to 1.2 volts for certain amounts of time. Okay, so 1.2 volts is virtually is a good way to kill fuel cells. So a fuel cell's open circuit voltage is more like 0.85 volts. We'll learn why in a minute. And if you hold it at 1.2 volts, you're in a region where carbon corrosion happens really quickly. So we didn't even talk about the impact of voltage on the rate of corrosion of carbon. We just talked about, you know, humidity, temperature, platinum loading, and the graphite, whether it's graphitized or not. So what they're plotting here is at 800 millivolts. You asked how much current can the fuel cell deliver, milliamps per centimeter squared. And for these fuel cells, around 200 to 250 milliamps per centimeter squared was delivered at 800 millivolts. But you can see this, the fuel cell that used Ketjen Black, 800 meters squared per gram, just dropped like a stone. So it didn't take long for this thing to just die. And at the same time, they're measuring what's called the surface enhancement factor. So what is this? This is the surface area of the electrochemically active platinum compared to the geometric electrode area. So what it means is, if you have a centimeter squared of electrode, you would start with 160 meters squared of platinum, 160 centimeters squared of platinum electrochemically active surface area per centimeter squared of electrode. And then you can see what happens, that just drops. And this is because of the carbon burn-off, where you're losing electric connection to these platinum particles. And this current density at 800 millivolts just tanks. So the one that's best here is the graphitized BP2000, okay, where it's very stable and you don't lose electrochemically active surface area. It's the stars here. You don't lose surface area very fast. So once people realize the importance of getting a stable carbon, fuel cell performance improved a lot, and the longevity of fuel cells improved a lot. So these are old data, but they turned out to be very important to the field.
Hi, Jeff.
Yeah.
How do you measure the surface enhancement factor?
Yeah, measuring the surface enhancement factor is very cool. This is probably worth spending a moment on. So I'll go to my document camera. Just trying to get there. Too many windows. Okay, I think you should see my document camera.
Yep.
Okay, so what you do is you measure a cyclic voltammogram. So you measure current versus voltage. And you can actually do this in the fuel cell itself. So you run how does this work again?
You mean how? Okay.
What's that? Is that Ron speaking?
Yeah. You mean what's running how? Like how does?
Yeah, I think you're running hydrogen on the negative on the anode, and you're running argon on the positive side because you don't want to create large fuel cell currents. So you have argon running on the positive electrode, and you have hydrogen running on the negative, and you measure a cyclic voltammogram. And what you measure is something that looks like this. It basically does nothing until you get down to around 0.2 volts. This is versus the standard hydrogen electrode. And then you see stuff happening. You see a nice signal, whatever it looks like. And if you keep going, then it shoots up like this because that's hydrogen evolution. When you go below 0 volts, you evolve hydrogen. And what this is under potential deposition of hydrogen, H2, on the surface of platinum. So what happens is the platinum surface gets covered with hydrogen. At first it goes down as atoms, and then it becomes molecules. And then when you go in the other direction, it strips off. And the area of this curve is proportional to the surface area of the platinum. The area under this curve is proportional to the surface area of the platinum. So how do you figure out exactly what the surface area is? Well, you take a polished platinum surface, polished atomically flat, and in a rotating ring disk experiment, you do exactly the same experiment, and you measure the size of this bump. And then you know that what the area of this bump compared to 1 centimeter squared is. So it's actually a simple technique that you can do it right in the fuel cell itself. So you can track what's happening to the catalyst in the fuel cell itself. And you know, by stopping the fuel cell operation, running argon on the positive side and hydrogen on the negative, and doing one of these sweeps. Does that sort of answer the question?
Yep, that makes sense, I think. Thanks.
I haven't thought about this stuff for a while, so I'm not that up to date in my brain. Okay, so let's go along. Make this big again. Okay, you should see the PowerPoint, I think. Is it true?
Yes.
Okay. Yeah, so a carbon support is not really ideal for the catalyst on the air side of a fuel cell, but it is what it's used, you know. And if you think about other things that you're going to think about using there, you're about 1 volt positive of standard hydrogen. So it's a very oxidizing environment. Metal supports don't work. They all corrode. Even platinum itself at 1.2 volts, the surface gets covered with platinum oxide, platinum hydroxide. So there's really nothing really ideal. So alternative supports have been considered. And 3M had a nanostructured thin film support that I'm going to tell you about because it's a really interesting story. That was once considered worldwide to be the best catalyst support for the positive electrode side. So around 2011, the US Department of Energy said, this 3M nanostructured thin film support is the world's best and everybody should use it. But in the end, it was never adopted. Okay, and I want to tell you what this stuff is and why it was so interesting. So this guy here, Mark Debe, he was a researcher in Building 201 at the 3M Research Center. And the Building 201 was kind of like Ivory Research Tower. So when I collaborated with 3M, I worked with people in Building 209, which was sort of like applied research and in the battery space, battery material space. And everybody over there said, you know, those guys in 201, they just do what they want. You know, they have coffee all the time. They're talking about their work. It's like sort of like a government lab almost, you know. And anyway, Mark, in the late 1980s, he discovered this stuff. Okay, this red pigment, whatever this word is easily vacuum deposited when subsequently vacuum annealed, a 1500 angstrom film transforms into a random array of crystalline whiskers of extremely high number density, 50 whiskers per square micron, uniformly oriented with their long axes normal to the substrate. So in the late 80s, Mark discovered this, and then 3M decided, well, we're not going to tell anybody about this because maybe this is useful for something. So it wasn't until like 6 years later that he published anything on this. And in the meantime, they realized that this could be used as a catalyst support. So this is what the molecule looks like. And like they say, you deposit a thin film of this on a substrate, and it's a flat film. And then when you anneal it, these whiskers grow. Unfortunately, there's no scale bar here, but he told you on the previous slide what the size is. Doesn't tell us the size. We'll see it on some of the next slides. And then they realized they could make a catalyst support out of this. So this is a SEM image of what they made. So let me explain this to you. So you can see the scale bar, 3 micron. So each of these little whiskers is about, 750 nanometers long. And it's been deposited on a microstructured polyimide support that looks like a repeating set of triangles. I'm going to draw you a picture on my document camera because I want to make it clear. And this is a top-down view of the whiskers here, okay? So I'm going to switch to my document camera for a second. You should see the camera. So what they did is they took polyimide, it's a plastic. It was not very thick, maybe 20 micron thick plastic film. And they made this triangular structure where this was about 20 microns, and this was about 6 microns. Okay, so 3M had all kinds of technology for doing this. And then they would deposit the Parylene red, that was the short name for this organic chemical, deposit it, and it would come down as a thin layer like this. I won't draw that everywhere. And then when you vacuum anneal this thing at 150 degrees C, you grow these little whiskers perpendicular to the surface, okay? Now, why did they put it on this corrugated support? Well, the reason is it's pretty fragile. And if you put them on a flat support like this, every time you go to handle it, you knock them off. But here, when you handle it, you only knock them off at the top of the mountains. Down in the bottom, they're nicely protected. So this was a pretty clever idea. Okay. So this is not a catalyst yet. Doesn't have any catalytic properties. So what you do is you put it into a sputtering machine and you sputter platinum down on it, or whatever you want. So here at Dow, we sputtered combinatorial mixtures of elements, platinum, nickel, cobalt, all compositions in a single run across an array of these materials. And then we built these into 64-channel fuel cells. We had all kinds of activity going on. But sputter depositing was really super cool. And I'll show you what sputter deposited stuff looks like. And then you have to ask the question, how do you get this into a fuel cell? Because the polyimide support is useless. You don't want that in a fuel cell. So I'll show you how that all goes. Yeah, so then what you do is when you sputter deposit the platinum on there, you can see these tiny little particles. Those are the platinum. So the guys at 3M called the organic whiskers, they called them whiskers. And these little platinum particles on the whiskers, they called them whiskerettes. Okay, so we're whiskers and whiskerettes. I mean, really, this is an amazing material science story. It really is. You know, this guy discovers this amazing, weird thing that happens, this self-assembly of these little whiskers. And then you decide you want to use it for catalyst. You can't support them on a flat surface, so you make this corrugated thing. Like, it's just so elegant and wonderful. It's incredible. And then what you do is you take that whisker-coated polyimide and you heat laminate it to the Nafion polymer electrolyte membrane. Okay, so here's the polymer electrolyte membrane, and here's the whiskers that have been heat laminated to the polymer electrolyte membrane. So we set up to do that here, and it's really trivial. You have a machine that you would use to make a student card, where you just have a photo on a piece of paper and you just run it through a laminator with plastic on each side and you get a hard student card. It was really that simple. You'd have your Nafion and then your catalyst on polyimide. You'd put a piece of paper top and bottom so that it wouldn't stick to the laminating rollers, and you just run it through. And this is what you would get. So this they called a catalyst-coated membrane. And everybody at 3M had all their jargons. You know, they had GDLs for gas diffusion laters, MEA for membrane electrode assemblies, and then they had CCM. CCM was a catalyst-coated membrane. So you're seeing a CCM here. And the catalyst layer turns out to be very thin, and the Nafion gets sort of pushed into it. So that means you get good contact of protons to the catalyst. This catalyst layer is, you know, almost perfect platinum on those whiskers, and that touches up against the gas diffusion layer on this side. So the electrons can get to the platinum whiskerettes easily. So you have almost full utilization of all the platinum that's in here, which is wonderful. The problem is that all the water that's generated on the positive side gets generated in this incredibly thin space. Whereas the catalyst layer in a typical carbon-supported catalyst situation, carbon black with platinum nanoparticles, that catalyst layer there would be more like 10 to 15 microns thick, you know. So here you're generating all that water in this tiny little space, so really easy to have flooding. So these catalysts gave a really good three-phase boundary, but it's really tough to run these things without flooding. Any questions about this?
So the reason why they didn't end up using it is the flooding problems and expensive processing.
The processing really wasn't that expensive by comparison to, you know, the cost of the platinum and so forth. It was pretty easy. You could make this stuff in a sputtering system, on a roll-to-roll sputtering system, which 3M had. So you had a system where the polyimide support moved underneath a thermal evaporator to put on the whiskers, and then it moved into a chamber, into an area where it's heated to 150 to grow the whiskers, and then onto a take-up reel, all within a vacuum chamber. So it was very slick. But the flooding really became the problem. Operating this stuff without flooding is virtually incredibly difficult. So let's take a look at this here. So this is an example that 3M put out showing the advantages of their support over the platinum on carbon. So what's happening here is the cells were doing CV cycles, I think between 0 and 1.1 volts. And while that's happening, the carbon support is degrading, and you're measuring the electrochemical surface area normalized to the beginning of the test. So the platinum supported on carbon, you had the burn off of the carbon and the crappy performance after a while. Whereas on the nanostructured thin film support, there was nothing to oxidize away. The organic material was perfectly stable, and anyway, there's so much platinum whiskerettes there that they contact one another. You don't rely on the carbon black to make the contact. So here, after huge numbers of CV cycles, oh yeah, they tell the CV range here, 0.6 to 1.2. The surface area is well maintained. So with this, you can make a really long lifetime fuel cell, incredibly long. Okay, any question about this catalyst stuff? I'm going to move now into the Nafion membrane.
Yeah, Jeff, just minor clarification. So when you guys did sputtering of platinum, how do you make sure that the whiskers are, like, I guess, conformally coated rather than just having platinum, let's say, on top? I'm just trying to understand how the sputtered platinum, you're able to get such good coating all across in this three-dimensional whisker, I guess.
Yeah, that's a really good question. So if you do thermal evaporation in a vacuum, it's kind of like a ballistic thing. The atoms are evaporated from a pool of molten material or sublime from a solid, and they move in a straight line because they're in a vacuum. Sputtering, though, is different, because in sputtering, you have, it's not a full vacuum. You have an argon plasma, and typically you're operating at, I don't know, maybe 10 millitorr or something like that. And it means that the atoms, when they move from the sputtering target to the substrate, when the atoms move from the sputtering target to the substrate, they're not moving in a straight line there, and they can penetrate down to the bottom. So here you see the whiskers, they're more heavily coated at the top, but as you go down, you still have whiskerettes on them near the bottom. But they kind of look like a baseball bat once they're coated. One end is pretty thick, and the other end, which would be the handle of the baseball bat, you can see it down here, it's not coated as well. But it coats pretty uniformly over 3/4 of a micron, and that was good enough. So it was pretty impressive that it worked so well.
Jeff, just also a follow-up comment on that. It's very it's unconventional that for the sputtered platinum atoms, they won't damage these organic molecules. Because normally, my experience with organic molecules is that those organic molecules are normally very susceptible to the ions bombardment. It looks like for these specific molecules, 3M found, it's like very stable during the platinum sputtering process. Just one comment.
There are no ions here. They're not ions, they're atoms. Atoms coming.
I see. Okay.
Atoms are coming over, not ions.
Okay.
Yeah. In sputtering, you have an argon plasma that hits a target and knocks atoms off, and the atoms come across. Okay, so let's move along. Okay, so let's talk about the polymer electrolyte membrane. So this is Nafion. It looks like Teflon, but every now and then there's one of these side groups here which has a sulfonate on it. And this can be made into thin films, and they're very strong. Nafion is very strong. And you can see there's a proton here that's bonded to this sulfonate end group here. So these things are proton conducting. The proton can hop from one sulfonate to the next to the next. But only in the presence of some water within the polymer. So this thing I want to call lambda. Lambda is the number of water molecules per sulfonate. Okay, and these Nafion polymers would typically operate well between about lambda equals 3 and 14 or something like that. So if lambda gets really small, the protons can't hop from sulfonate to sulfonate. There's sort of like, if you like, nothing in between to help them move along. So you can see it's called perfluorosulfonic acid PTFE copolymer, and here's the fluorosulfonic acid part here. So you'll get, an acid will give you good proton conductivity for sure, good ionic conductivity, and this membrane will as well if it's somewhat wet. So the properties of Nafion: highly chemical resistant, mechanically strong, can be made into very thin films down to 50 microns. They can be made as low as 10 microns nowadays. This is from the book that I mentioned earlier, so it's quite old. They're acidic. They can absorb large quantities of water, and if they're well hydrated, so if there's water in them, hydrogen ions can move quite freely within the material. They're very good proton conductors. So this is sort of a cartoon that shows the long chain of the polymers, and the water collects around the clusters of the sulfonate side chains. And you want to have these waters overlapping so that the proton conductivity is really good. And here's a graph that shows you the conductivity versus relative humidity. It's a log scale for conductivity for different temperatures. So remember, the fuel cells are going to operate up around 80 degrees C. So this would be 70 degrees C. 343 is 70, 333 is 60, and 318 is whatever it is. So you can see that the conductivity is pretty much temperature independent, provided that you're humidified to the same extent. And the relative humidity, once it's lower than 10%, the conductivity just drops off to nothing. And even when it's 30%, conductivity is much smaller than when it's much higher. Okay. So you should be thinking to yourself, okay, this is interesting, because in a fuel cell, I have to have good conductivity from the membrane, which means I need to have water around. But if I have too much water around, I'll flood the positive side. So there's going to be some real tricky balance here about operating a fuel cell. Like, how do I keep the membrane humidified and not flood the positive electrode? And if you're thinking that, you're thinking about the right thing, because it's a tricky thing. And then here's another plot that shows lambda, which is the water to sulfonate ratio plotted versus relative humidity. So you can see that how the water versus sulfonate ratio depends on the relative humidity. And then you can take this graph and plot what you really want, which is how the conductivity varies with lambda, which is the water to sulfonate ratio. And now you can see that when lambda is small, you're getting deep trouble, and the conductivity kind of saturates at larger values of lambda. So you'll have liquid water around when the relative humidity is 100%, and at that point lambda is about 13 or 14. So the maximum value of lambda that you can get is 13 or 14. That's what you would get if you took Nafion and you put it in liquid water. You'd get a lambda of about 13 or 14. So this turns out to be very important for fuel cell operation, and something, it's one of the things that you don't learn about if you just take a quick look at fuel cells. You say, oh, they're marvelous. But now you learn a little tricky to operate. Okay, any questions about this?
I have a question. So how reversible is the Nafion wetting, for example? Let's say you flood your fuel cell, you want to dry it too much, you dry the Nafion. I mean, can you wet it again and run it again, or then it's doomed? Like, the Nafion shrinks and contracts and everything breaks apart.
Well, it doesn't shrink and contract in a fuel cell because it's in a stack and it's well compressed. Turns out to be very reversible, Ron. It's really incredible. You can flood your cell, and then you can, in a few minutes, you can flow low humidity air and low humidity hydrogen to it and dry it out. And you can over dry it and have lousy performance because the conductivity is down here somewhere. And then you can rehumidify the gas flows and move back into this region. I mean, we're going to come to this in a minute. Our exploration and operating fuel cells here at Dalhousie with the 3M nanostructured thin film support was an exercise in really understanding water management. in the fuel cell stack. And it got to the point where we just absolutely were pulling our hair out, which is one reason why I have no hair. And I'll tell you the story of how we overcame that, which is kind of interesting. Yeah, I think we'll just do one more slide here. Yeah, we'll just do one more slide because it's a good place to end after the next slide. So, you know, what's the consequence of this membrane conductivity on fuel cell performance? So you can see about 0.3 Siemens per centimeter. This would be a decent value of the conductivity. So if you have, what is a Siemens per centimeter? Well, if rho is 100 ohm centimeters, then sigma is 1 over rho. It's 0.1 Siemens per centimeter. So if you don't know what a Siemens per centimeter is, that's what it is. So we have a 50 micron membrane, and you want to know the resistance per centimeter squared. Resistance is resistivity times the length divided by the area. So the resistivity is 1 over sigma. So you put that in, you work it out, and you get 16 milliohms would be the resistance. So if you're running 1 amp per centimeter squared as typical current density for a fuel cell, it give you a 16 millivolt drop in the membrane. So that's pretty darn small, and that's good. But if the membrane dries out, you know, then you're in deep crap, because then the resistive drop in the membrane is enormous. So the membrane has to remain humidified for decent fuel cell operation. This is a good place to stop before we get on to electroosmotic drag next time. So any final questions here?
So, is this type of membrane used in commercial fuel cells?
Absolutely it is.
Okay. And how are they controlling the humidity for those products?
Well, that's why you have to come to class, because you're going to learn that over the next 2 more lectures, how it's all done.
Cool.
Yep.
So there is a solution. So good to know.
Oh yeah, there's a solution. Of course there's a solution. But it's important to realize that this is not like, you know, just dropping things into a fuel cell stack and magic happens and it just works without any thought. It's been a lot of careful thought to make these things work.
Jeff, we don't have any other alternatives to this Nafion layer?
There's equivalent membranes that are made by other companies that are very similar. They all require humidified conditions. They're all this type of polymer with, you know, some kind of acid type of thing in there that conducts protons in the presence of water. They're all quite similar.
I see.
The name Nafion is patented by DuPont or something, right? It's their product name, right?
Yep, it's DuPont material. So 3M had its own membrane that was quite similar to Nafion, and they would give us Nafion for free. It was incredibly expensive. I don't know, something like $1,000 a meter squared or something like that. It's ridiculous. And so they would give it to us for free, and they would also give us their membrane, which had very similar properties to the Nafion, but was available at lower cost to people outside. For us, it was free. Yeah, but anyway, you can see this is an interesting problem. How do you control the membrane humidity and prevent flooding?